Hello students, this is lecture 2 of MTH 201. In the last lecture, we discussed geometry of points and vectors in R3. Today we are going to talk about an operation on two vectors which is called dot product. So let us first define what dot product of two vectors is. So let V be equal to V1, V2, V3 and W be equal to W1, W3 be two vectors. So remember last time I told you that we are going to use triangular brackets to denote vectors, right? So the dot product of these two vectors V and W is denoted as V dot W and it equals V1 W1 plus V2 W2 plus V3 W3, which is multiplying the corresponding components. So the x components are multiplied plus the y components are multiplied plus the z components are multiplied. So you can see clearly that it doesn't matter what vector comes first, in the sense that w dot v is same as v dot w, right? So this dot product is also known as inner product or scalar product, but we are going to use the notation, the terminology of dot product. It is a scalar number, right? So when you multiply these corresponding components and you add them, you get a number, you get a real number, right? So this gives you input two vectors and what you get out is a real number. Let us look at a few properties of dot product. So first property is that dot product of a vector with itself is greater than and equal to 0. Why? That's not difficult to see. So if V is equal to W in this equation, then W1 is V1, W2 is V2, W3 is V3. So you get V1 square plus V2 square plus V3 square. So it's a sum of squares of real numbers. So it has to be greater than or equal to 0, right? And when will it be 0? If and only if all the three components V1, V2, V3 are 0, right? So this is an important property of dot product. Second, if you take scalar alpha and you first multiply alpha with the vector v and then take the dot product, that's same as multiplying the scalar alpha with the dot product of v dot w. That comes immediately from the definition of dot product. Similarly, if you multiply beta to w and then take dot product with v, you get the same thing. Okay. Third, if you add two vectors and then take dot product with a third vector, then you can distribute the dot product. So u dot v plus w is same as u dot v plus u dot w. Similarly, if you add two vectors and take dot product with a third vector, you get the same thing. Okay. So if you notice, I told you that it doesn't matter what the ordering is, right? So this u plus v dot w can be written as w dot u plus v, right? And then you can use the first property. Okay. So once I give you this property, this second property comes from the first property. Okay. And finally, this is something that I have already discussed. If you take two vectors u and v, their dot product is same as v dot u. Okay, so the definition of dot product is very simple. It's just adding component wise products of the two vectors. Okay. So now let us define the concept of length of a vector and distance between two points in R3. So let V be equal to A1, A2, A3 be a vector in R3. Its length or norm is denoted by, so you put the vector V and you put these double vertical lines on either sides. That's the notation, and it equals square root of the sum of squares of the components. Okay, but you remember this is nothing but square root of dot product of V with itself. So what is the length of a vector? It's nothing but square root of the dot product of the vector with itself. Okay, and square root is all right here because we saw that V dot V is greater than or equal to 0. So you can take square root, right? So this is a well-defined number. Now from the definition of length, you can see that if I multiply this vector V by alpha, a scalar, and I take the length of the vector, new vector alpha V, that's nothing but absolute value of alpha comes out and you multiply by the length of the vector V. So that is also not difficult to see because if you multiply alpha by V, then each of these A1, A2, A3 gets multiplied by alpha. So you get alpha square times this sum, right? But when you take square root of alpha square, what you get out is modulus of alpha or absolute value of alpha. Okay. A vector V is said to be a unit vector if its length is 1. Okay. So this is an important concept. Unit vectors are quite crucial. You will see at several stages in this course. So a vector is said to be a unit vector if its length is 1. So the standard basis vectors that we defined, you remember I was 1, 0, 0, J was 0, 1, 0 and K was 0, 0, 1. They are all unit vectors because if you calculate their lengths, they are all equal to 1. Okay. Now, if you start with a non-zero vector, you can divide the vector by its length and then it becomes a unit vector. Why? Because if you take length of this new vector where alpha is equal to 1 by the length of V and you use this property, right? So what you get is length of V by length of V is equal to length of V divided by length of V, which is equal to 1. But for doing this procedure, you want to make sure that V is non-zero because if V is a zero vector, then distance of V is 0. I'm sorry, length of V is 0, right? So if length of V is 0, you can't divide V by a 0, the number 0. So it doesn't make sense. So you do this only when V is a non-zero vector. And when we divide V by its norm or its length, we say that we have normalized V. Okay, so given a non-zero vector, you can normalize it by dividing it by its length. Okay. Now let us talk about distance between 2 points. So let V and W be two vectors. The distance between their endpoints or heads P and Q is given by, you remember last time we defined vector joining 2 points P and Q, right? So if P and Q are the heads of these two vectors, then P and Q coordinates are defined completely, right? They are nothing but components of V and W respectively. So the vector PQ is nothing but W minus V. So the length of this vector is nothing but the length of this vector W minus V. Okay. And this is a pictorial representation of length of a vector. So suppose this point is the point. Okay, so this bold vector is the vector v that is given to you. What is its length? It's nothing but this distance, okay, which is this quantity that we have defined. So how do you get this quantity? You can see that if I drop a perpendicular from this point to the xy plane, I get the z coordinate, right, which is nothing but a3. So this height is a3. Now once you are here, what are the coordinates of this point? The coordinates of this point are a1, a2, 0, because you are on xy plane. So I'm sorry. So if this point is a1, a2, 0, then its distance from the origin is square root of a1 square plus a2 square, right? Okay. And this distance, which is the distance between the origin and the point a1, a2, a3, is nothing but square root of a1 square plus a2 square plus a3 square. So this is what we are talking about here, okay, which is this quantity. Okay, so now let us discuss an example. So the question is, normalize the vector v from the point 1, 1, 1 to the point minus 1, 0, 4. Okay. So let us first compute the vector. How do you compute the vector from this point to this point? It's just this minus this term wise or coordinate wise. So you get minus 1, minus 1, 0, minus 1, 4, minus 1, which gives you minus 2, minus 1, 3. So this is the vector. But you have to normalize it. How do you normalize a vector? You calculate its length and divide the vector by its length. So if you compute its length, its norm of v is equal to the sum of squares of its components, which is minus 2 square plus minus 1 square plus 3 square, which is given by this, which is square root of 14. Okay. Now how do you normalize the vector? You divide the vector by its norm. So which means that you divide each component of the vector by its length or the norm, and this is what you get. So this is the representation in terms of triangular brackets, and this is what I have written in terms of ijk, which also we saw last time. So this is in terms of the standard basis vectors. Okay. If a vector has length 0, then it is nothing but the 0 vector, right? And the length of a vector v is same as that of minus v, right? Because you see, when you take squares, negative sign does not play any role. So therefore the length of a vector v is same as length of the vector minus v. Okay. So now let us try to understand the geometrical meaning of dot product. So let theta be the angle between two vectors u and v. Then their dot product is nothing but norm of u times norm of v times cosine of theta. Okay. So therefore, if both u and v are non-zero vectors, then these two quantities, norm of u and norm of v, are both non-zero. So you can divide this entire equation by norm of u, norm of v, and then take inverse cosine on both sides. So you get theta to be equal to cos inverse u dot v divided by norm u, norm v. Okay. So pictorially what we are saying is the following. So suppose you have two vectors u and v and you take the angle theta between them. Okay. So now you will wonder which theta I should take. There are two thetas, right? One is this angle, other is this other angle, right? 2 pi minus theta. So the angle that you take is the one which is smaller. Okay, so that's how you get this condition. Okay, so I'm not, according to this picture, this is the smaller angle, so this is my theta. Okay, also you can see that it doesn't matter whether you take u dot v or v dot u, so it doesn't matter what is the positioning of these vectors. So this relationship that is written here is independent of the vectors u and v, the positions of u and v. Okay, you decide theta according to the angle which is smaller than the two. There are two angles between the vectors, right? You take the smaller one. Other observation is that if u and v are unit vectors, then theta is cosine inverse of u dot v, right? So for two unit vectors, the dot product is nothing but cosine of theta. Okay, so this is the geometrical significance of dot product of two vectors. Okay, so let us prove this. It's a proof that uses trigonometry. So let us look at this picture again. You have vectors u and v, and remember this third vector which is the third side of the triangle which is formed by u and v is v minus u, right? You see where you end, you look at that vector that comes first minus which is here, right? So v minus u. So you consider this triangle. Now using law of cosines from trigonometry, length of this side is equal to length of this side plus length of this side. I'm sorry, I'm missing out the squares. So square of length of this side, which is norm of v minus u square, is equal to length of this square, which is norm u square, length of this square, which is norm v square, minus 2 length of these two sides product times cosine theta, where theta is this angle. So this is the law of cosines from trigonometry. Now I'm going to use the relationship between norm and dot product. So the left hand side becomes v minus u dot v minus u, right? And this norm u square becomes u dot u and norm v square becomes v dot v. So this can be rewritten as this in terms of dot products. Now you consider the left hand side of this, which is v minus u dot v minus u, and you use distributive law for dot product. So I did not mention distributive law, I'll mention it in the notes. But you remember one of the properties that we looked at about dot product, there it was dot product of a vector with sum of vectors. So that's what we are using here. So v minus u dot v minus u is v dot v minus u minus u dot v minus u. Now again you use distributivity, you get v dot v minus v dot u minus u dot v plus u dot u, right? Which is equal to v dot v minus 2u dot v. Why 2u dot v? Because v dot u is same as u dot v. And the final term is u dot u. So if you compare these two equations, two terms cancel, right? U dot u cancels and v dot v cancels, and minus 2 cancels, and what you are left with is u dot v is equal to norm u norm v times cosine theta, which is what we wanted, right? Hence we obtain the result. Okay, very good. So now let us look at an application of this result, which is called Cauchy-Schwarz inequality. This is a very important inequality in vector calculus. So for any two vectors u and v, mod of u dot v is less than or equal to norm u norm v. And this less than or equal to is actually equal to in two cases. One, if either u is a scalar multiple of v or v is a scalar multiple of u, if one is a scalar multiple of another, or if one of u or v is zero vector. Okay. Now if one of u or v is zero vector, then it's easy, because if you take dot product of a vector with a zero vector, you just get 0. And the right hand side is also 0 because length of 0 vector is 0. So you get 0 equal to 0. So this part is easy. Okay. So let us prove this. So using previous result, if theta is the angle between the two vectors u and v, then u dot v is norm u norm v cosine theta. Right? Now you take absolute value on both sides here. You get mod of u dot v is equal to norm u norm v, which is already non-negative, so modulus does not play any role, times mod of cos theta, right? But mod of cos theta is less than or equal to 1. Therefore, mod of u dot v is less than or equal to norm u norm v. So I will write this intermediate step in the notes. But what we are using really is take modulus on both sides and use the fact that mod of cosine theta is less than or equal to 1. So you get this inequality. Now when will these two things be equal in modulus? If cosine theta in modulus is equal to 1, which means that cosine theta is equal to plus 1 or minus 1. So theta has two possibilities, one is 0, other is pi. Only at these two values in the interval 0 pi, cos theta is plus 1 or minus 1, right? So now if theta is either 0 or pi, this means that either two vectors are in the same direction or they are in the opposite direction. But they can be scalar multiples of each other, right? So, I'm sorry, yeah, so when the angle is like this, either 0 or pi, either the vectors u and v have no angle between them, meaning they are in the same, they are pointing in the same direction. So you can write one as a scalar multiple of another, or if theta is pi, then the one is in the opposite direction of others. So you can again write one as a scalar multiple of another, but with a negative sign. Okay, so this is the proof for Cauchy-Schwarz inequality. Okay, now finally let us look at the concept of orthogonality of vectors. So you have seen this term orthogonal in linear algebra, right? Which meant perpendicular. So it's the same concept here. So two non-zero vectors u and v are said to be orthogonal or perpendicular if their dot product is 0. Now this is not surprising, this definition, because from the previous result u dot v is nothing but norm u norm v cosine theta, where theta is the angle between them. So if theta is equal to pi by 2, then cosine pi by 2 is 0. Therefore, u dot v is equal to 0. So this definition is not surprising. It says that when this is true, when theta is pi by 2, then you say that the vectors are orthogonal or perpendicular. So they are actually perpendicular, as you know geometrically. Now, if you look at these three unit vectors I, j, k, they are mutually orthogonal, right? Because why are they orthogonal? Because I dot j is 0, j dot k is 0 and I dot k is 0. All the pair dot products are 0, right? And any collection of three non-zero mutually orthogonal vectors is known as an orthogonal system. So it need not be these three vectors. You can take any three vectors which are mutually perpendicular or mutually orthogonal. Then you call it an orthogonal system. So let us stop here.